Hi everybody, this is Nafish. Today I'm going to go over beamforming and DOA, which is direction of arrival estimation. And basically we will try to implement that in Python. I'm going to start and at the very basic level, very beginner level. Okay. So first, before I go into Jupyter Notebook, I will try to explain this one pager. Okay, just the concept a bit. I'm not going to get into a lot of equations. Okay, so let's have a use case. Okay, so basically think of a autonomous vehicle which has a radar, this black vehicle right here, which is the host vehicle. Okay, and it is mounted with the radar, and that radar has one transmit antenna and three receive antennas. Okay, and the job of this radar is to measure the angle of the targets. So let's say the white vehicle is a target vehicle which is in the adjacent lane. Okay, and the radar has to measure the angle of it. Okay, so the radar will transmit a electromagnetic wave. It's going to hit the white vehicle. Okay, and it's going to get a return signal. And from the return signal, we had three receive antennas, right? So all the reflections will not come at the same time. Okay, because there is a spacing d, so they are interspaced, all these three receive antennas, and there will be a time delay in these receive antennas. Okay, so basically if you look into this diagram here, in the first element there will be no time delay because this is it will get the reflection first, and compared to the first element there will be a time delay on the second element and third element. So what is beamforming? Beamforming is just we need to account for all these time delays. So we'll apply some weights on this receive antennas, and sum it, and then we'll have a output. And from the output, we will calculate the angle of this white vehicle, which is called DOA. So these two terms, beamforming and DOA, direction of arrival, is kind of like we always talk at the same time, because it's beamforming is just applying the weights, and then from there you have to calculate the angle of interest. Okay, so let's get started in Jupyter Notebook. In NumPy as NP, this is for numerical calculations. We need this NumPy library, and then import matplotlib.pyplot as plt. Okay, this is for plotting purpose. So I have these two libraries, and then we are going to divide this simulation in 4 steps. So we will create a transmit signal, then we are going to have a receive element, receive signal, then we are going to have the beamforming, and then DOA, or direction of arrival estimation. Okay, so basically the angle of interest. Okay, now first part is generating a transmit signal, and we are just going to keep it very simple as I mentioned before. So just going to have a sinusoidal wave. Okay, so Tx is nothing but our amplitude, and then exp exponent, then j the complex number, then 2 times pi times f times t. Okay, so this is the equation I think most of us kind of very much familiar. Okay, now the amplitude is just going to be normalized amplitude of 1, and exponent we have to write np in front of it because we are getting it from numpy library. Same with the pi, np dot pi, and this complex number we have to have an integer in front of it, so just putting 1 so that numpy recognizes it as a complex number. And these two variables, frequency is not defined and the time vector is not defined. So let's say frequency is 1 megs. Okay, and this is the down converted frequency. Okay, so the sampling frequency, let's have 10 types of the frequency f. Okay, and then time vector, right? So time vector, for time vector we need to have the start of the signal, which is let's say 0 seconds, and then we need to have the time duration, how long the signal is going to stay, or how long is the duration of the signal. Okay, so let's say 10 milliseconds. Okay, so this is td, and then we'll need to have the number of samples. Okay, and definitely we need to have np dot linspace in front of it. So basically what it's going to do within this time duration of 10 milliseconds is going to generate the number of samples we are going to provide. Now samples is not defined, so samples is nothing but we have the sampling frequency going to be multiplied with the time duration. Okay, so I think we are all set. And one thing here I just wanted to show you, commenting out this TX equation, we run it and then have a look into the samples. Okay, so you see there is an error right here. Okay, the reason of the error is, like, you see the samples is float number because you are multiplying here, right? So it becomes a float number, so we need to put integer in front of it because the linspace function expects integer number. Okay, and then we will run this equation. I think we are all set here, so there is no error now, and let's plot it out. So ple.plot, what's our time vector t, and then we have that tx. Okay, now you see the samples is like 100,000, so, and also this is imaginary number. Okay, so I should have taken the real part of it. Okay, so this warning is from the coming from the imaginary number, but you see it's not easy to visualize these many samples, right? So we are just going to take first 100 samples, okay, here, and also from 0 to 100. Okay, and just to avoid this warning right here, just going to take np dot rel. Okay, close it out here, and let's visualize our sinusoidal wave. Okay, so this is our sinusoidal signal right here, and in all signals we will have some noise incorporated, and this noise can be generated from the system itself, or when it's when the signal is traveling through the medium in the environment, we can have some noise. So just we'll add some noise into it. Okay, so let's say our noise n is np dot random dot normal. Okay, 0 mean, and let's say 0.01 standard deviation, and then np dot shape of this transmit signal. Okay, tx. Okay, so this is the real part, because our signal has both real and imaginary part, right? So I'm just going to copy this thing again and then add it with a complex number here, right here. Okay, the same thing. Okay, so our noise will also have the real and imaginary part, and then our transmit signal becomes txn. Okay, is tx plus the noise. Okay, and let's visualize txn. We'll have some distortion probably here. It's not visible because the and the noise probably is very small amount, so we'll just add 0.1 here. Okay, and then okay, you see some distortion in the transmit signals in some points. Okay, so we have the signal, a kind of realistic signal with noise incorporated. Okay, now let's start with the recipient. So this signal is going to hit the target vehicle, okay, and we will going to have a receive signal, right? And that's what we are going to simulate right now. Okay, so the equation to generate the receive signal is Rx is equals to steering vector transpose of it and then multiplied by the Txn. Now there are two questions, what is this S steering vector and why we are taking the transpose of it. Okay, so I'm going to explain these two things. Okay, so let's define the steering vector first. So remember we had 3 receive antennas, right? So let's say we had transmitted this signal, so I'm just going to copy that one, okay, and going to paste it 3 times. So 1, 2, 3. Okay, because both of the 3 antenna elements will receive the reflected signal, right, which is the transmit signal, but there will be some delay added to it. And this steering vector, the final form of it is going to be a -1, or sorry, minus component in front of it. Why is that? Because it is going to hit the target and you are looking at the reverse direction, right? So in the transmit, when we are generating the transmit signal, there was no minus in front of it because you are looking at the front direction. Now you are looking at the receiver end, so there will be a minus in front of it. Okay, and then these two things, F and T, will be replaced by the D, which is the inter-element spacing. Okay, remember in our lecture we said like there is some inter-element spacing. Okay, so what is this D? In general, D is 0.5. This is the electrical distance. This is not the physical distance though. So how you are going to get the electrical distance? You have to take the physical distance and divide it by the frequency. Okay, so you get the D. And in this case, we are assuming like the it's equidistance. Okay, 0.5. Then the next parameter that will come into is the which element you are looking at. So nr minus 1, let's have a parenthesis here, nr minus 1. Okay, so we have three elements, right? First, second, third. So when you are looking the phase delay, and you are taking the phase delay with respect to the first element 1. Okay, basically you can just see like this term is going to be 1 minus 1 is 0, this is going to be 1, right? This term, this coefficient or the weight, basically the first element is always going to be 1 because you are measuring the phase with respect to the first element. Okay, but this is the equation, this is how it is derived, so I'm just writing it down. Okay, and then we need to have the angle from where the signal is coming. So np dot sine, then this angle is going to be in radians. Okay, because we are dealing with the exponents. Okay, now what is this angle in radians? So let's say our angle, the target is located at 10 degrees. Okay, so angle in radians is in we have to divide it, we need to divide it by 180 degree. Okay, and then multiply by np dot pi. Okay, this is how you convert it into radians. Okay, so we have it now. You can say like, hey, this 10 degrees, you already know the answer, right? No, this is in case like, you know, you are getting the return but the system doesn't know it. We have to generate a signal, we embed this angle into the signal. Okay, but the system doesn't know what is the which angle you are getting the return from. We'll derive that later. Okay, so we have this radians right here, np dot sine. Okay, so this is basically the final form of the steering vector. Now let's fix the other two components. So this f and t will go away, replaced by the inter element spacing d, which is already defined. Then we have the next term is nr, receive antenna number minus 1. So you are looking at the second element right here, so you will have 2. Okay, and this term will be multiplied by np dot sine and then angle in radians. Okay, and the third term right here, again we need to replace these two things and then multiplied by d, and then this is our third element, so 3 minus 1. Okay, and this has to be multiplied by np dot sine, then angle in radians. Let's see where is there is anything wrong with the parenthesis here. 1 2. Okay, we should be all set. Now let's visualize s first. Okay, so run it and let's see s. Okay, so this is the weights. Okay, so basically steering vector is just the weights we need to we have for this receive antenna elements. Okay, so the first element itself, when you are comparing, there is no phase difference, and this is the phase shift for the second one, and this is the third one. Okay, so when you are creating the receive signal rx right here, you have to multiply the transmit signal with this coefficient so that you get the appropriate time delays. Okay, so that's what this equation is doing here. This is a matrix multiplication, and we need to do a couple more things here. I'll just show. Np dot shape, let's have the shape of this signal, s, and this is a list, so we have to convert it into numpy array because we are going to do matrix multiplication, right? So let's say s is nothing but np dot array, and then we take s. Okay, so now run it, and then let's measure the shape of s. You see, this is now an array. Okay, so we need to do the same thing with the transmit signal. Okay, so txn, txn, and then the input is also txn here. Okay, so run it, and now we would like to see the shape of this txn as well. And this is because I'm trying to explain why we're having the transpose here, right here. Okay, so you see, for any matrix multiplication, you need to have the first this s here, s parameter right here. We have three columns, and this number of columns needs to match with the number of rows in the second matrix. But this is not the case here, right? So this is 3 here, this is 1 here. That's why we need to take the transpose. Let's take the transpose. And now you see the column is 1 here, and the row is also matching, so you can do the multiplication in this case. So I will run it. Okay, no error here. So let's add some noise with these receive signals, because we'll also get some environmental and system noise added into it. So I'll just take this equation right here. I'm just going to modify it a bit. So noise in the receiver end, nr. Okay, and we need to have the shape of this rx signal. Okay, and then this rxn is just going to be rx plus nr. Okay, now let's plot it out. So plt dot plot, and then we have just going to plot the first 100 samples. Okay, so 0 to 100 here, and then we have this rxn. Okay, and did I show the shape of this? So this is going to be 3 rows and 100,000 columns. Okay, so basically 3 rows is coming from 1 2 3 receive antenna elements. Okay, so if you would like to visualize the first element, you have to put 0 here. Okay, all the samples, and then you need to take the samples from 0 to 100. Okay, and also need to take the real part of it. So np dot real. Okay, so this is the first element. I'm just going to copy it a couple more times. So Ctrl C, Ctrl V, Ctrl V, and now this is the second element, this is the third element. Okay, and let's plot it out. Okay, okay, there probably some error. I will just run it from the beginning again. Okay, okay, now it's all set. I think there was something going on, but anyways, if you look into the phase here, the starting position right here, so the blue line, this is the first signal, right? This is the 0th element, or the first receive antenna element. Okay, and then this is the second one, this is the third one, and you see the signal is starting a bit late here, a bit late here. So this is kind of showing the delay we are getting due to the spacing of the receive antenna array. Okay, so this is our receive signal, and you see some distortion, which is for the noise. Okay, so now we have our transmit signal, receive signal. Let's work on the beamforming. Okay, so I'm just going to erase this one, erase this one. Okay, now for beamforming, just going to write down the final form of the equation. Okay, so and this is going to be the delay and sum beamformer. Why we call it delay and sum beamformer? Because you are you are compensating or applying the weights for the delay and then summing it up. Okay, so that's why it's the delay and sum beamformer. Okay, so let's say ds bf, delay and sum beamformer, and the equation for this is we have to take the steering vector. Okay, and then you have to take the conjugate of it, and then the transpose. Why need to take the transpose, already explained earlier, and then the whole thing is going to be multiplied by the receive signal rxn right here. Okay, so now one thing is here, our beamformer doesn't know the answer, right? So it has to sweep the beam electronically. And what does that mean? Let's say we had a radar, right? So radar field of view is, let's say, 90 degrees. Okay, what does that mean? It starts the scanning from minus 45 degrees to plus 45 degrees. So beyond these angles, it doesn't see anything. Okay, this has the field of view from minus 45 degrees to plus 45 degrees. So what this beam, this steering vector, we need to do a loop here. Is going to go into each and every angle of this field of view and try to find the best match or the highest signal is going to get. Okay, and since we had a signal at 10 degrees, it should get the highest match or highest signal around that angle. Okay, so this is our radar field of view. Let's convert this into radians, right? Because we had exponent in the in right here. Okay, so radar, I think the radar spelling is wrong here. So radar FOV, and let's say this is in radians, right? And then into we have to so we are going and checking in each of the angle, right? So np dot lean space. Okay, and our starting value is minus 45 degrees. It's going up to 45 degrees, and how many samples we have? So the interval, if you take 1 degree interval, okay, 1 degree interval going to give you 90 points. Okay, so this is going to be 90 points here, but let's say we need more resolution, so we'll just take 0.5 degree interval, which is going to give 180 points here. Okay, so 180, the more resolution you are going to get, the finer match you are going to get. Okay, we will just check out, we'll just do some things later, show that. Okay, so let's say for this case we have 180 points, and then we have to convert this into radians. So np dot pi divided by 180 to convert it into radians. Okay, before doing that, just wanted to show you the steps. So let's erase this part first. Okay, okay, and then run it, and then let's look into the radar FOV. Okay, okay, and you see the steps is 0.5 degrees, so we are going to get more resolution than 1 degrees here. Okay, now convert this into radians. Okay, so np dot pi divided by 180 and multiplied by this whole array. Okay, so then run it, and then everything in radians now. Okay, so we have our values in radians. Okay, so let's work on the for loop now. Okay, so for I in radar FOV in radians. Okay, and then what we need to do is we need to write down this S right here. Okay, you copy this and you paste it right here. Okay, so this is our S Okay, and I have to put it here. Okay, now this angle is in radians, so angle sorry, radar FOV in radians. Okay, so this for loop is going to take the values, but this is going to be I here. Okay, so you are doing a for looping right here. Okay, so I here and I here, so you are going to change the values 180 times. Okay, and try to find the best fit. Okay, so and then also I need to do one more thing here. I need to convert this S into I need to convert this into numpy array. Okay, so S is np dot array, and then S. Okay, and this is ts. Okay, I think we are all set, but it's going to update the results every time, so we have to have an array to keep the values. Okay, so empty array, so let's say results is an empty array, and we are going to keep this all these values 180 values here in this results. So results, okay, dot append. Okay, and then you're going to append the value dsbf. Okay, and since we need to calculate the power, we're going to take the square of it and doing a mean. This is how you calculate power. Np dot mean. You can also take a variance here and you will get the power. This is how we do it for the time domain signal. That's right. So let's work on the direction of arrival estimation. Okay, so we have the beamforming output. Okay, so DOA. Now first thing first, from here we have to take the absolute value. Okay, so results is np dot absolute value of this results. Okay, so we are just taking the absolute value, you run it, and let's set the shape np dot shape of this results. It's going to be 180 points here. Okay, right here. Okay, so to get the direction of arrival, okay, DOA, is we have to take so we have to take the maximum value, right, as I mentioned before. So np dot argmax. Okay, and then we need to have the results. Okay, and let's visualize the DOA first, which, so this is going to give you the index. Okay, so you run it, and so 112. Okay, so this index, this is happening, so you have to get the index this 112 to get the angle. So you need to have this one right here. Okay, radar FOV. Okay, because you have all the angles here, so you write it down here, and basically you are going to take this index 112 from it. Okay, so let's run it. So this is the value. Okay, now this is in radians, right? So DOA in degrees. Okay, what you do is this one, then 180 divided by np dot pi. Okay, now run it, and we have to visualize it. So degrees, so 11.31. Okay, so this is our final output. And what is the angle we had? So 10 degrees. For some reason we are getting 11.31. So let's plot out it. Okay, so ELT plot, just wanted to see the signal. Okay, so we have the angle which is right here, it's in radians, so you take that. Okay, and then you have to multiply by this, right? So you copy that one, paste here, and then multiply. Okay, so you have everything in degrees, and then in y-axis you have to have these results, right? You have to take the results. Okay, and here you have to divide it by the max value to normalize it. So max of results. Okay, then you should have the plot. Let's have the plot. So this is our this is the plot we are getting. Okay, so you can see the beam is kind of spreaded, and there are a lot of angles falls into it. So but this is where you are getting the peak. Okay, Um, Now, what happens if I take some more samples here? Okay, first let's change the angle a bit. Run in. What is the answer now? 17.84. Okay, the peak is right here. So if we take more points, whether that improves the performance, let's see. Let's say we are taking 360 points. Okay, run it out. Okay, so 25.44, what was our angle? Is 15. So it's really didn't help. How about we do not add any noise and see how is the performance? Okay, so is this is kind of very much affected by the noise? Let's see. So we run it. So our input was 20 degrees, right? Our angle was 15 degrees, and now you see it's 14.9. So it's a very close match, right? Let's have some more angles. So you see how it was impacted by the noise. Okay, so this is one of the disadvantages in this delay and some beamforming. Okay, it's kind of um, very much impacted by the noise we get in the environment. Okay, and also you see the spreading here. It's kind of like, if we have two targets, it will fall within this spreading, and it will have hard time to find out where the peak is located. Okay, so you can see, like, it's there is no noise, and it's kind of very much performing or giving us the expected results, 9.9 in this case. Okay, and now let's say if we want to check out the angle 30, how it is doing at the edges. This is another disadvantage in the edges. It's kind of, doesn't always give you the right answer, although in this case it did. But you see, like, there is another peak which is very close to this one, and you might get a negative angle sometimes, because this peak is very close to this one. Okay, and in the edge cases you have grating lobes popping up, and sometimes you will get some totally wrong angle. So there are a couple of disadvantages, and in next lecture we are going to play with this all these parameters here. Okay, some other parameters, and try to see how this behaves. Also in the plotting section, what plt dot figure, let's have this figure fixed size is equals to, let's say, 10.8. We'll have the plt dot grid is on, okay, by default, and plt dot x and going to have np dot a range, and let's say we are going to have tick marks right here from 0 to, let's say, 45 degrees. Let's say we need 10 here. Okay, 10 times. So let's run it, and oh, okay, I forgot parenthesis here. Okay, let's run it. Okay, so you can see the peak is right there, right around 30. Okay, I can do some more changes. Let's say 13. I'm just trying to find a angle where it kind of misinformed, or give us wrong answers. So 13 is kind of, I think it's picking up 13. 12.99. Let's have 17. Okay, let's run it. Waiting for the answer. 17. Okay, you see here, minus 45 degrees. So this is one of the answers it's giving, which is wrong. Okay, because the peak is occurring right here at minus 45 degrees, although you have a peak right here at around 17 degrees, right? So basically, since it finds the first peak right here, it gives us the answer. And this is like, because you are having two peaks, so one is it's kind of perplexed. The system is perplexed, like which one to pick. Okay, and it's giving you the negative peak right here, which is the wrong answer. So this is one of the drawbacks. There are many. We'll discuss in the next lecture.